So the next speaker is Laco, which will make an interesting presentation about the method of repairing pre-stress tendons through reinjection of grout. As Eduardo said, Laco couldn't be present today, but he gently left us a pre-recorded video of his presentation. He will not be able to answer questions live, but all the participants are invited to put them, as we'll send these questions to Jan and we'll reply to each one by email. Now, let me say a few words to introduce Jan. So Jan Laco is a chartered bridge engineer with a broad range of technical experience. His technical expertise covers bridges and highway structures, design and assessments. Jan is profiled as an expert for post-tensioning systems, design and their durability.
Good afternoon, everyone. My name is Jan Laco, and I'll be giving the presentation on behalf of all authors. And the chapter concerns repair of pre-stress tendons through reinjection of grouts. The chapter is mainly text only, so all the photos provided in this presentation were given kindly by Mr. Hrapa from Dubrastav. Installation of bonded tendons is often linked to difficulties mainly related to cementitious grout injection. There are many cases where grouting was carried out inadequately. The primary cause for inadequate grouting are inexperienced staff or poorly defined quality control procedures for the grout injection process. Problems with the grouting procedure cause the structure's deterioration after several years of service. The presence of voids in grout facilitates corrosion propagation, which weakens the cross-section of the tendons. Consequently, cracks develop due to overall structural weakening and changes in static behavior of the structure. Repair of pre-stress tendons should be carried out following detection of the defects in the ducts or deterioration of the tendons. Underestimating deterioration associated with these defects can result in changes in structural behavior and potentially in structural failure. Before significant structural behavior changes are perceptible, minor defects can be observed. These are likely to include rust-stained water leakage from the structure adjacent to tension strands, which potentially indicates voids and active corrosion process. Let's talk about grout characteristics. Cement grout for injection of pre-stressing tendons should comply with national standards. Key considerations include stability, flowability, and chemical composition. The recommended values are fluidity immediately after mixing from 9 to 25 seconds, fluidity 30 minutes after mixing 1.0 times D naught to 0.8 times D naught. Volume change at rest for 24 hours from -1% to +5%. Bleeding should be less than 0.3% at 3 hours and no bleeding occurring after 24 hours. The mechanical resistance to be reached should not be less than 30 megapascals at 28 days or 27 megapascal at 7 days, if it is proposed to estimate the likely 28-day strength at 7 days. It is vital to achieve resistance identical to that of concrete structure. The exact values may be prescribed by national standards, annexes, or guidelines. Grouting of tendon ducts must be done with particular care to ensure they are completely filled, as residual pockets of water may otherwise remain in the ducts, where its exposure upon freezing can cause further cracking in the structure. Therefore, the specification needs to state that no bleeding is acceptable. Good practice is to minimize water-cement ratio for the grout. Various standards and guidelines recommended that the water-cement ratio for cementitious grout should vary between 0.38 to 0.42. However, water-cement ratios near the upper boundary may cause deterioration of the grout, primarily due to insufficient swelling of the grouting material during hydration process. Therefore, it is recommended that the WC ratio does not exceed 0.4. Water-reducing agents may be used to enhance workability and compaction. Occasionally, cement for pre-stressing grout is specified in accordance with FIB Guide to Good Practice, grouting of tendons in pre-stressed concrete. However, more commonly specifications are produced in accordance with national standards. Admixtures should comply with the requirements of the national standards. In order to protect the pre-stressing steel from corrosion, specific requirements regarding chloride, sulfates, or other substances added to the mix and cement should be defined. The grouting procedures depends on tendon layout. The duct fill rate should be between 5 meters per minute and 15 meters per minute. The grout vents should be positioned based on the tendon layout and the nature of cement grout. Nationally and internationally published documents may specify vent locations. If toxotropic grout or vacuum-assisted grouting methods are used, vents are not required. The aim of grouting operation is to completely fill the tendon, ensuring the strength to be fully embedded to avoid any attack from the infiltration of corrosive agents. When the attack by an aggressive environment, high chloride, sulfate, or sulfur content has already started, an intervention through reinjection of grout should prevent further deterioration. The strengths must be located in a passivating environment or in an environment with a low content of aggressive ions. If the environment contains a significant level of aggressive ions, mitigating measures must be carried out prior to the reinjection. For bonded pre-stressing tendon, the hardened cement grout must also demonstrate sufficient mechanical properties to ensure that bonding between the strands and the concrete structure occurs. The details concerning the final protection of the pre-stressing strands must be defined at the project design stage in order to determine the position of the upper vents and the lower purging vents. When the tendons are horizontally marginally deviated, it is necessary to consider vents at least every 40 meters. In the presenting tendon layouts presented below, the vents positions are located to avoid presence of stagnant water in the ducts and the formation of air pockets during grout injection. A configuration with vents is shown in the adjacent figure. The grout progression inside a duct with a generally deviated profile was identical to behavior achieved in many model tests undertaken at a scale of 1 to 1. The observation from the test suggests grout progression velocity ranges for each type of tendon, and the position of nozzles, purging or injection valves to avoid or to eliminate trapped water or air pockets by means of grout reinjection. Furthermore, it is well known fact that water from chemically unbalanced grout tends to gather at the high points of the ducts, thereby constituting a risk of concrete containing the experiencing bursting force due to formation of ice or alternatively the creation of a vacuum if water has been absorbed by the grout. Entrapment of air in voids located behind the grout progression from during injection, which happens mainly on the legs of the duct sloping downward relative to advancing grout front, also constitutes a risk of corrosion. To achieve adequate grouting of pre-stressing tendons, it should also be considered that any non-homogeneous grout in contact with strands causes migration of water by capillary flow and filtration through the interstitials between the strands wires. The volume of segregated water is proportional to difference in pressure existing between the upper and lower points of the ducts. The most critical case concerns highly deviated or vertical tendons where water accumulates at the upper surface of the grout. The required equipment for the execution of vacuum reinjection is as follows. It's a vacuum pump, volume meter, pressure gauge, mixing and injection pump unit, air compressor. All devices must be certified, maintained, and regularly tested. Let's talk about stakeholders' role and qualifications. The structure's owner should provide all relevant available information from previous interventions, assessments, original design projects, and construction records. The owner may specify additional requirements for service life of the strengthening elements, minimum or increased structural performance, durability of the strengthening element, warranties, stipulations not to affect the service of the structure during interventions. The owner is also responsible for quality control measures, inspections, monitoring, and maintenance. An overall understanding of the structural behavior is essential to ensure the adequate design can be carried out and the repair procedure proposed. A designer should possess an adequate understanding and experience of performing structural assessments of post-tension concrete structures and bridges. In particular, the designer must understand the difference between static behavior of bonded and unbonded tendons. A designer should be able to develop a structural analysis in combination with section resistance calculations to determine the adequacy of the structure. This should consider bonding condition and positions of the prestressing. In a situation where reinjection of grout cannot solve the structural durability problem and combine intervention utilizing reinjection and other repair strengthening methods, tendons replacement can be adopted. This is particularly effective when heavy tendons deterioration is observed. However, the combined intervention requires careful work sequencing to prevent undesired, unfavorable adverse effects on the structure. Only a contractor certified to carry out post-tension installation works is permitted to make interventions upon a functional pre-stressing system. The contractor should be aware of the importance of the pre-stressing system within the structure and its importance to the integrity of the structure. The contractor should have available all devices required for tendon repair and is responsible for all aspects of their operability. The contractor is liable for the compliance of the materials used with requirements of the design and specification. The applied materials must comply with the required standards and specification. Where the applied material does not comply within the design, a material approval request should be issued to the designer. Where there are areas of concerns, the scale and severity of the defects should be identified by the engineer in charge, who should also decide on the appropriate repair method. Existing conditions of the structure must be considered during this process. As part of this process, it is necessary to estimate the severity of the damage and estimate whether permanent structural changes are likely to have occurred. The structure manifests permanent changes through cracking of the affected area, deterioration of other structural elements such as ducts, strands, or anchors, and through excessive deflections. Once this has been identified, the repair scope and other interventions should then be developed and specified. Designers should also determine the criteria and set out the parameters for replacement of a tendon. Replacement will be dependent on the geometry and other conditions of the structure, including extent of grouting in the tendon, accessibility to the affected tendon, presence of additional ducts on the structure, and impacts on the operation of the structure. Full reliability level of the structure is envisaged after successful repair operation. However, in some instances, there will be a decrease in the structure's reliability after repairs to the structure. This may be due to corrosion in a strand which has not been repaired or other damage to the structure which were not rectified during the repair grouting. The design engineer should then be able to determine any possible decrease to the structure's reliability. Relevant documents applicable for post-tension material and testing requirements are listed on the slide. There are European standards and FIB bulletins providing guidance for pre-stressing. Full bond between strands and embedding grout can generally be assumed after successful grout repair. bond allows pre-stressing strength utilization up to its yield strength at ULS. The challenge is in estimating the remaining pre-stressing force within the affected strengths. Where the direct force is not measured on site, the estimate of the pre-stressing force will be dependent on the predicted structural behavior from the analysis model, the condition of the structure, and the experience of the design engineer. The decrease in the tendon force can be estimated based on expired service life of the structure, taking into account an estimation of the immediate and long-term pre-stressing losses based on classification of the installed strength type. The designer should consider possible cross-sectional loss due to previously identified pitting corrosion of the strengths in the area affected by voids. The presence of cracking or excessive deflections identified prior to the intervention will also provide an indication of the stressing state within the strengths. Where cracks have developed, it may be necessary to reassess the structure considering section properties for correct cross-section. Supporting documents for structural assessment and repair may be as follows: historical construction and pre-stressing records from contractor, previous similar design projects including drawings and conclusions, inspection and monitoring reports, previous intervention records, repair technological process report, and other relevant standards. Let's talk about execution. Although different approaches can be adopted towards increasing or reaching the original design stressing force, it is usually preferred to inject grout due to cost efficiency if the required safety level can be achieved. Common grout injection practice is vacuum grouting. Once all voids are identified, any inadequate grout must be removed. Hydrodemolition is not generally recommended for the removal of the delaminated grout. Pumping dry air through the tendon can dry the delaminated grout and remove moisture, thereby limiting corrosion process. The most critical point in the intervention operation is air tightness of the system itself, along with the tightness of the equipment and its accessories. Therefore, multiple tests are required to ensure the adequacy before the reinjection process can be initiated. The success of vacuum grouting is dependent on maintaining vacuum in the sheet. The duct must be properly sealed and free from water. External air must be prevented from entering the sheet with the grout. And the following phases of work should be carried out with care: installing and sealing the cap, removing the remaining oil, sealing test with compressed air, and vacuum holding test to be done prior to grouting operation. System trial should be carried out before any work. Where vacuum-assisted grouting of pre-stressing tendons is to be carried out, it is necessary to clean all the affected zone prior to injection to ensure there is no remaining water present and to improve overall effectiveness of the grouting operations. The injection procedure is then applied in the following stages: verification of the airtightness of the system using compressed air. Deteriorated material should be removed and reprofiled cracks should be repaired using injection with fast-set epoxy material. Calculation of the void volume based on the volume of compressed air. Vacuum reinjection. The volume of supplied grouting material has to be greater than the measured volume of the voids during the tests. The vacuum is applied to the valve fitted at the extremely linked with the pump by sealing the valve. The vacuum pump is activated and the vacuum is applied to the system. Once the vacuum is created in the void, the grouting mortar can be introduced into the void by switching the three-way valve. The grout is then pumped through the grouting hose to avoid capturing air in the nose. Once the pressure in the void is maintained and the desired level without significant variation in the injection valves are to be closed to prevent leakage of the injection mortar. The plastic hoses can be removed after 36 hours. At this time, a visual control must be completed by the grouting team and supervisor. The visual control must be recorded in a protocol. Injection mortar is a homogeneous material of cement, water, and additives. The injection mortar must must comply with national requirements and standards. Every contractor executing this kind of work should use a certified mix design for the injection grout. The mix design should include the type of cement, the water-cement ratio, and the definition of the additives used. All the content should be in accordance with a valid declaration of conformity issued by the procedure. Due to the lack of time, I only introduced the case study. The case study is concerning Varna-Enon bridge, where tendons were recruited. The case study was provided by Virginia Department of Transportation and the designer. The Varna-Enon bridge crosses the James River 20 kilometers south of Richmond. The bridge consists of parallel precast box girder substructure, which contain 480 tendons with grouted post-tension strengths, as well as 26 stay cables supporting the center spans from the two towers. And this is the end of presentation. Should you have any questions, please send me an email on laco@dphase.sk. Thank you.
Unfortunately, the audio was not the best in this case, and I apologize for that. I hope you could understand the main aspects, but if not, I also remember that that the audience can still put questions. That these questions will send to Jan, who will reply them by email. Finally, I would like to thank you to acknowledge Jan Laco again for his presentation.